Welcome to number theory. Today, we are diving into Euler's criterion. Imagine you are a bouncer at an exclusive nightclub called the Perfect Squares. Checking every single person to see if they belong would take forever. What if you had a magical ID scanner that instantly told you who gets in and who gets rejected? That is exactly what Euler's criterion does for numbers. Before we look at the scanner, we need to know who is trying to get into the club. In number theory, a quadratic residue is just a formal term for a perfect square in modular arithmetic. Specifically, an integer a is a quadratic residue modulo an odd prime p if there is some integer x that, when squared, leaves a remainder of a. If no such number exists, it is impossible to reach a by squaring anything, and we call it a quadratic non-residue. Now that we understand what a quadratic residue is, let us look at how Euler's criterion tests for it. This formula is our magical ID scanner. You take your candidate number A and raise it to the power of p minus 1 divided by 2. If the result is congruent to positive 1 modulo p, the number is a perfect square and is allowed in. If the exact same calculation results in negative 1, the number is a non-residue and is rejected. Let us visualize this process. You can see the flowchart starting with our inputs, the integer a and the odd prime p. We feed them into the central decision engine, which calculates a to the power of p minus 1 over 2. The modular arithmetic forces the output down one of two paths. A result of 1 guarantees the number is a perfect square, leading to the green box. A result of negative 1 guarantees it is not, leading to the red box. This elegant theorem eliminates the need for exhaustive guessing. Before we move on to the proof, let us see this formula in action with a concrete example. We want to determine if the number 2 is a perfect square modulo 7. This means we are asking if any number squared leaves a remainder of 2 when divided by 7. We identify our candidate A as 2 and our prime P as 7. Next, we calculate the special exponent required by the theorem by subtracting 1 from 7 and dividing by 2, which gives us a target power of 3. Now we apply this exponent to our candidate number. We raise 2 to the power of 3, which yields a straightforward result of 8. This is the core calculation of our scanner. Finally, we divide our raw result of 8 by our prime modulus 7 to find the remainder. 8 goes into 7 exactly one time, leaving a remainder of exactly 1. Because the final answer is 1, the mathematical test has flashed its approval. 2 is indeed a quadratic residue modulo 7. Let us try a different number against a slightly larger prime. We want to determine if 2 is a perfect square under modulo 11 arithmetic. Our strategy remains exactly the same. We identify our prime modulus p as 11 and our candidate a as 2. We first calculate the test exponent by subtracting 1 from 11 and dividing by 2. This gives us a final test exponent of 5. This exponent is the key to unlocking whether our number is a residue or a non-residue. With our exponent calculated, we now apply it to our candidate number 2. We multiply 2 by itself 5 times, which gives us a raw value of 32. While this number is easy to calculate, it is currently too large for our modulo 11 system. We must reduce it to find its true modular value. We divide 32 by 11. 11 fits into 32 exactly 2 times, which accounts for 22, leaving us with a remainder of 10. We have a remainder of 10. But in the context of Euler's criterion, we need to look at this slightly differently. In modular arithmetic, a remainder that is exactly 1 less than the modulus is equivalent to negative 1. Since 10 is exactly 1 less than 11, we can write it as negative 1 modulo 11. Because our final result is negative 1, the test has officially rejected the candidate. There is absolutely no integer you can square to get a remainder of 2 when dividing by 11. Now that we have used this formula successfully, let us understand where it comes from. To prove why this works, we start with a famous rule called Fermat's little theorem. This theorem states that for any prime number p and any integer a not divisible by p, raising a to the power of p minus 1 always leaves a remainder of 1. It guarantees that the calculation will always perfectly wrap around the modular clock to land on 1. By simply subtracting 1 from both sides of the congruence, we shift the equation to equal 0. This means the massive number on the left side is a guaranteed multiple of our prime p, setting up our next step. This small algebraic shift we just performed sets the perfect stage for factoring. Because p is an odd prime, the number p minus 1 must be an even number. This even exponent is incredibly useful because it allows us to cleanly cut the exponent in half and apply the classic algebraic rule for the difference of two squares. This creates two distinct bracketed terms. Because our prime number p divides the product of the two brackets, it must divide at least one of them individually. If it divides the first, the expression equals positive 1. If it divides the second, it equals negative 1. This factorization is the critical leap that makes Euler's criterion possible. To prove which signal means what, we now assume our candidate number a is actually a perfect square. This means it equals x squared for some unknown integer x under our specific clock arithmetic. We substitute x squared into our test exponent. The 2 from the square and the 2 in the denominator cancel each other out perfectly, leaving x raised to the power of p minus 1. According to Fermat's little theorem, any valid integer raised to p minus 1 must equal 1 modulo p. Therefore, we have definitively proven that every true perfect square will always yield a 1 in Euler's criterion, completing our proof. So, we have proven that the criterion holds. This brings us to an important question. Why do computer scientists care so much about this? In the modern digital world, finding perfect squares in modular arithmetic is the hidden engine behind secure communications. Algorithms like RSA constantly manipulate massive prime numbers. Before a computer wastes precious processing power trying to calculate a complex square root, it uses Euler's criterion as a lightning-fast gatekeeper. Without this rapid sorting mechanism, modern public key cryptography would be far too slow for everyday internet use. Let us review the key takeaways from today's lecture. We learned that quadratic residues are simply perfect squares under the rules of modular arithmetic. Euler's criterion gives us a direct mathematical test using the special exponent p minus 1 over 2. If the calculation yields 1, the number is a perfect square. If it yields negative 1, it is not. Finally, we saw how this elegant theorem forms a crucial foundation for the cryptographic security that protects our digital lives. You now understand the mechanics of Euler's criterion.